Can somebody decide Zarif he needs to, I don't know, use another or log in again because he keep on, saya dah admit banyak kali. I admitted him many times, but still he requested to enter.
Oh, okay, I will tell him.
Okay. Tak ada masalah dia. Okay. So, have you all watched the videos?
Yes, madam.
Yes, madam.
Okay, because it's very important and your assignment will be based on that. And a lot of questions in the final also based on that. Wait a second, I will just video for a while. Okay, sorry for that. All right, so okay, so you watched the videos and before. Okay, Mirza, it's okay. You can close your camera. I think before we start, just to lighten the mood, let's watch a video. Okay. How do I share this? Share. Share computer sound. Okay. Can you see?
They're all gone. It can't.
Can you see? Can you see and nampak?
Yes, madam.
Okay, thank you. So let's watch this.
They're all gone. It can't be true. They're all gone.
All gone.
What would the world be like without semiconductors? I'm Nicole Scott. I'm the co-founder of Mobile Geeks and a video journalist. Today I'm at Bosch doing a little bit of investigative reporting, trying to find some semiconductors. I'm going to meet Emma, so hopefully I'll be able to learn all about semiconductors.
Hi. I'm Nicole. Yeah, great to meet you, Nicole. Hi, my name's Emma and I'm an engineer here at Bosch in Reutlingen, which makes me an expert in semiconductors.
Perfect. I have a million questions for you.
That's great. Should we get started?
Yes.
Brilliant. Let's go inside.
It looks very techy.
Yeah.
So I had a terrible dream last night that I lived in a world without semiconductors.
Well, that must have been truly awful because they are everywhere.
They're even in my smartwatch, right?
Yeah, sure. They're in your smartwatch. They open your garage door when you come home at night. They're in your toothbrush when you brush your teeth. They heat your house up in the morning. They are literally everywhere.
Now, can you show me what it looks like? Can we actually see inside my smartwatch?
Yeah, sure. Of course we can. Shall we open it?
Yes. Ah, we have lab coats.
Yep. Grab a coat and grab some safety glasses.
So where exactly are we?
So today we're in the training lab.
So you actually got it open. Here
Yeah,
it is.
we got it open and now we can see all the semiconductors that are inside.
And so you have a tiny little chip there.
Here we have one of the chips from the back side of this PCB. This is an inertial measurement unit. It has 3 gyroscope and 3 acceleration sensor axes, so real moving parts in here on a microscopic level, and an electronic circuit which interprets all of those signals.
So how exactly is a semiconductor made?
Well, did you know basically they're made out of sand?
No.
So we start off with quartz sand. This quartz sand is melted down to create a really pure silicon base. Then we pull a monocrystalline crystal out of this sand, saw it into strips, which are then called wafers. And with these wafers, we then go into a production facility like we have here and build complicated 3D structures for electronic circuits, but also mechanical structures.
So there's all of those sensors and a tiny brain in that very small chip?
Yes, it does.
That's really impressive.
Yeah, and it's not just impressive in your phone or in your watch, we also have them in cars.
Really? Can we take a look? Now this is a really cool car.
In every modern car, there are hundreds of semiconductors all working together in the safety systems like airbag and electronic stability control, but also for comfort functions like air conditioning or heating, going all the way around to finding out where you are. Just simple navigation is also semiconductors.
Cool, I didn't know there were so many semiconductors in a car. Yeah, thanks so much for having me.
You're welcome. It'd be great to have you again sometime.
Oh, you know I'll be back. I think the most interesting part of my day was learning how semiconductors are made and how they fit into everything. They're really, really small, and they're really in all parts of our society. They're everywhere.
All right. Okay. Okay, did you manage to watch it? Boleh dengar?
Dengar,
Yes.
Madam, dengar.
So just to warm up, it's just a video showing that semiconductor devices or electronic devices made of semiconductors are everywhere, and it's nearly impossible to live without the anything on semiconductor electronics nowadays. And nowadays there are before this most of it are mechanical. Okay, now we are moving on to electronics. Even cars, before most of it are mechanical cars. Everything inside are mechanically based. So now they are moving to electronics. So everything to even controlling the gear are from the electronics. So electronics are becoming more important, and even for cars, right? For the the mechanical department, they are teaching automotive, right? And it's in mechanical department. Now they have to revise a lot of the curriculum automotive to include the electronics. So it's no longer purely mechanical, it's a mix. So you are doing CIE mostly, right? And com. So everywhere actually needs electronics engineer. It depends on how much you know before the company will hire you. Okay, so that's enough for the introduction for today. There's some motivation for us to learn this. So let's go back to the video that you watched. Any question? So we'll start with that. If no question, I assume everybody understands, so we can move to the next topic. Wow, this is amazing that you understand everything.
Yang part yang tak ada suara tu je lah.
Okay, part yang tak ada suara tu, which part you don't understand? As specific.
Macam dekat apa first video tu kan ada 6 point madam kan?
Ada
Yang tak ada
6
suara
point.
tu ada 6 point. So macam yang tak ada suara tu daripada point 4 sampai 6.
Okay, so
Saya tak sempat stated lah which apa exact tu.
So you don't understand, kalau tak ada suara tak faham Saya kalau tak ada suara saya boleh faham juga macam mana. so you watch and you don't, okay never mind. So let's see, kat mana saya draw benda tu. Semicon, the one that I drew. Not this one. Kat mana? Oh, Microsoft whiteboard. Sekejap. But the most important from the videos, the really important are the one with the energy band diagram. You'll be using that for your assignments and for your final exam. The one in the beginning is for you, is like a basis for you to understand the energy band diagram. The energy band diagram, you need to remember every single thing and understand every single thing. Why is it there, right? So let's see, where is it? Any go? I think this one. Okay, I will share my iPad. Okay. Okay, this one, right? Yes, no?
Yes madam. Starts from the drift current until the total current.
From the drift current.
Point number 4.
Point number 4. Okay. So, okay, drift current. So basically, when you have the built-in voltage and electric field, remember last time when you have that, therefore you have drift. You have drift current. And this drift current, so, and this drift current has the direction of given here. So drift current is in the same direction of the electric field. Okay, so therefore you have drift current, and this drift current, if you look, is the opposite direction of the diffusion current. So diffusion current going to the right and the drift current going to the left here. So if you put it in terms of equation over here, number 5, the drift current in thermal equilibrium, in equilibrium where everything stabilized, the drift current, the diffusion current equals to the drift current. Okay, so but equal by opposite direction. So therefore, that's why if you look at the PN junction, not all the not the whole PN junction will be depleted, because it will be cancelled out by diffusion. So you have diffusion at the same time, you have drift in the same time. So it will come to equilibrium, and when that achieve equilibrium, this equation is true. The drift and diffusion current, the magnitude is the same but the different direction. Therefore, if you total you total up the total current inside the semiconductor PN junction, it will be 0, because it's just a total of the drift and diffusion. since the drift is the opposite direction, so that's why the total current is 0. So if you hold any PN junction or diode, you pegang dia tu kan, you will not find it, there won't be any current because the total current is 0. Although actually there are 2 currents that are flowing inside the device. Okay, any question? No?
No, madam.
You understand now? So
Madam.
any more question? I given you a lot of videos. You
Madam.
understand everything? If you understand everything, I will ask you question then.
Question.
Yes, Mohaimin.
Okay, so in the reverse bias, you said there is a small current, right? Very small current due to the drift, right? Due
Yes.
to the drift, not diffusion. So basically, so why does drift? The current is due to the drift. Why not diffusion? Because even you can see that the graph is one is very high and one very low end. The graph you draw the graph. Okay.
Yes, yes.
So even the concentration is different. Why doesn't hold from the P go to the what to the N? Because
Okay, in order to better explain that, that's why we have to use the energy band diagram approach. You know, in life, dalam hidup ini, there are many theories and there are many ways of explaining the theories. For example, when we talk about atom before, we talk about the Neil-Bohr theory, the Neil-Bohr apa dia panggil itu, representation, whereby it's just a nucleus and then you have ring, right? But later on, when they found out they cannot explain certain things that happens with the when they do experiment, they cannot explain using that theory. So they make up another theory. That's why there's a quantum mechanics in order to explain why light can be diffracted, right? Why you have fringes, because there's like it's behaving like it can behave like a wave as well. So the similar, because you know at the moment we started very simple, then we go more complicated in order to explain things that we cannot explain using simple model or theory. So the first model is the structure model that I'll teach. I was saying this electron, you can see going there, right? The drawing. Next model is the energy band diagram, which can explain better the drift current. So I will go through now. We'll share my screen with you again. Good question though. Okay, can you see my screen?
Yes.
I'm using another software now. Keep on changing, trying to find the best. Okay, so we want to talk about drift current now. At reverse bias. Besar sangat ni punya ni. At reverse bias, the drift current. Normally, when you have a lot of current, it's due to diffusion, because it's diffusing majority carriers. Drift current normally is due to the minority carriers. Okay, so for example, let's draw the energy band diagram. So in the exam and also during your assignment, you need to explain in terms of energy band diagram. So you should be able to draw. In the final exam, I'm expecting you, or in the quizzes, I'm expecting you to be able to draw the energy energy band diagram by your own. So in reverse bias, right? So we always start with the P. Okay, so you have your P over here, and your the P, the Fermi level. Don't forget the Fermi level. So then you have the P, and then you have the N. Okay, and because it's reverse bias, the N is below the P. Something like here. Okay. Jauh sangat ni. Okay. Okay, so then then you draw the Fermi level for the N, and then you just what do you call it? Sambung the 2P and N junction. So this is reverse bias. So how do I know? Because the Fermi level of the N is below the Fermi level of the P. Okay, if it's at zero bias, the key is the Fermi level of the P and N should be equal. It should be in the straight line. That's zero bias. Reverse bias, the Fermi level of the N should be lower than the P, and Fermi level for the forward bias, the Fermi level for the N should be higher than the P. Okay, so that's the indicator. Now what happens is in reverse bias, okay, so in reverse bias, this height is actually the energy, which is the potential energy, which is related to the potential energy from the built-in voltage. So it's actually so we can convert this into, actually this is the built-in voltage plus the voltage that we apply for the reverse bias. Okay, the reverse bias voltage is in the same direction of the built-in voltage. Okay, so I can draw another one here. If I copy this, so if I just how do I do this? I cannot. Okay, dia tak boleh cut sekali lagi. Never mind. So if I were to draw this again, dia tak nak padam. Oh, I see. Because I paste it in terms of, okay. Sorry, I'm learning this. So I think because I paste it in terms of image. Let's try again. Be patient. Alright, so then, okay, now I can delete. So now so if I draw like this, brothers and sisters, if I draw like this, what is the difference between figure A and figure B? Anybody?
Figure B, you apply more reverse voltage. Good.
So just by looking at the what do you call it, the figure, you know that actually figure device B has been subjected to higher reverse bias voltage. Okay, so let's use figure B because it's more dramatic. It's okay, it's easier to see. So if you look here, so if you, it means that this is reverse bias, right? Reverse bias, it means that we are connecting this to this, P to the negative and N side to the positive of the voltage. Okay, and we have majority, we think about majority carriers. In the end, the majority carriers are electron, right, here. And in the hole, the majority carriers are, so in the P, the majority carriers are hole. And electrons are, I remember my supervisor always said, the electrons are like balls, balls. The characteristic, the hole is like a bubble. So holes always wants to go up, electrons, balls will like to go down. So if you can see, like the electron, to overcome this is difficult because you have a higher potential to overcome. So it's like a higher hill to climb. And the same as the hole is difficult. So that's why in reverse bias, it's like diffusion is negligible. You cannot get a lot of current due to the majority carriers because the carriers or the free carriers cannot overcome the barrier. However, okay, to diffusion, now I want to talk about the question, your question on the drift. So just drop off. Now we talk about drift. If you remember, you still remember, in P, in the P material, you have electrons. Do you have electron in P or no? Yes. Is it majority or minority?
Minority.
Yes. So you have a few of the electrons in the P side, and what do you call it? Hole, minority of holes in the N side. And when the electrons go over here, you will see a hill. So it will go and drop. And this is due to drift, right? Because it's due to the potential hill. The hill is the electric field and the voltage. So the electron will drift down and the hole will drift up. And because it's minority, so the drift current in reverse bias, is it a lot or little?
Little.
Little. So that's why. Wait a second. Okay, let me share my screen again. Okay, can you see my screen?
Yes.
Yes.
So that's why if you draw the IV, the forward, you have a lot of current. This current is due to diffusion and due to the majority carrier. But in reverse bias, ni pun exaggerating, it's actually, if you really see in a linear plot, you don't see any current. It's because it's very little. It's like micro current, micro amp or nano amp. So you see a very small current, and this small current is due to drift, due to the minority. And then in the video that you watch also, I talk about breakdown. Okay, does that answer your question?
So in the first video, when you say there is the current is negligible or almost no current, it does not include the scenario of breakdown, right?
No. We talk about normal reverse, not entering the breakdown yet.
Okay, noted.
Okay, any more questions? No?
Madam,
Yeah.
I have some question on the breakdown mechanism part.
Okay.
Okay, as you mentioned in the video, it is two kind of breakdown mechanism, which is the first one Zener and the second one is avalanche.
Yes.
For the Zener part, what is the Fermi level? Fermi level in the Zener is outside outside of the covalence and valence bond.
So your question is?
Why is the Fermi level is outside?
Okay. Thank you for your question. The Fermi level is outside because it's heavily doped. So for example here kan, okay, I remember I told before, I think in the class we talk about the doping. So like, so remember last time, it's another page. So we talk about the doping. So if let's say this is P and P plus. P plus meaning it's higher doping. So sometimes we can have another P plus plus. If you see plus plus too, it means that more doping are put. Okay, so P and P plus. So how does the Fermi level will look in these two energy band gap or band diagram? It will look like, so the P over here will be something here like this, yeah, closer to this conduction, this is valence, conduction, valence, and this because the figure A, figure B. So figure B has a higher doping, therefore the Fermi level should be closer to the valence band. So when you dope it even further, a lot, it can happen that the Fermi level is figure C. The Fermi level can be inside the valence band. It just show that it's the doping is very high. But there are consequences if you dope it very high. You know, doping is basically, if you remember from, if you look at the slides or the book, you know, you have atoms of the semiconductor. And then when you dope it, you're actually adding extra atoms to the original semiconductor material. And this can make the, you know, it will disrupt the lattice. Disrupt. It will disrupt the lattice. So you can disrupt the lattice. When it disrupts the lattice, we can increases defects inside the structure. So there's, you know, in life, there's always limitation. So not everything good. You keep on adding the doping. Yes, it will increase the free carriers. However, it will disrupt the lattice and therefore may increase the defects inside the structure. Okay. Have I answered your question?
Yes, madam.
Good. Any more question?
Last question for me.
Boleh.
Regarding the avalanche part. The key point that you mentioned in this avalanche is the impact ionization, right? Okay, yeah. So my question is, as you mentioned in the video, the impact ionization happens when the electrons hits the atoms and it splits into a pair of electrons and holes, right? Yeah. So does it also happens for the holes?
It doesn't split, it releases.
Doesn't split, it releases. Okay, my bad, sorry.
Okay.
Does it also happens when the holes hit the atoms?
Good question. So yes, I didn't mention the video. Yes, it's the same. The hole can do the same. but the rates at the impact ionization rates of the electron and hole are different. Remember, electron and hole have different masses. How it if you do further study on impact ionization, you know, just to share, in my group in Sheffield before, it's a special group. It's the group, the research group is called impact ionization group. Why? Because for the past, I think 20 years or 30 years, their work, their research are all concentrating on impact ionization. So they find out the impact ionization rate for most of the semiconductor materials. So in the world, not many experts. So they are like, so my group was like two of the antara yang tiga yang teratas lah in the world on impact ionization. They are very niche, and they do very detailed study on different material have different impact ionization rates, and the impact ionization rate for the electron hole for different material also different. And the study is important because engineers can use this rate in order to design their detectors, which is some of you will be doing it for your assignment. Okay, so so yes, there's different, the rate are different. So but both electron hole can cause pneumonia impact ionization. Okay.
Okay, madam, and what happened after the electrons or the holes hit the atom? What happened after the release of the pair of electrons and hole?
Okay. Okay, good. It's not clear in the video? I can't remember my video. I've been doing it like 2-3 years ago. It's not
The video
clear.
stopped until kinetic energy.
Really?
Yes.
Can
Yes.
you
Yes.
Yeah,
It doesn't explain about the holes.
Yeah, we just like you are wondering a little
Okay,
bit after.
bagus. At least you
After
know that you have something to ask in the class. Okay, let's see. Let me share. Saya bersyukur saya buat video tu long time ago. I did the video for my FIP students and my master student because I need to keep explaining the same thing many times. So that's why I made the video. Now alhamdulillah you also can use it. But I didn't watch it again, so I don't know if there's error. Hopefully there's no error there. If you think that if there are things that you don't understand, maybe there's error, so you should ask. We human, we make errors. Okay, so can you see my pad now, iPad?
Yes, madam.
Now, the question is, what happens after that, right? Okay, let's draw this. Can we use the existing? Let's copy. Okay, senang hidup sekarang. Copy paste. Okay. All right. So okay, so let's assume this what do you call it? This PN junction is in breakdown mode. So what happens is I will just delete things that are not needed. Okay, whenever you draw in the final exam or quiz, make sure you label everything. Even though I might forget to label here, but in the exam, be extremely careful. Make sure you label the conduction band, balance bands of all. Make sure you label the energy band gap, because sometimes okay, another question. Sekarang saya suka buat soalan yang pelik sikit, like a bit just for excitement. For example, if I say this now up to date, maybe I should talk about, maybe I should introduce you to now on heterojunction. Have you heard about the word heterojunction? Yes, no, don't know. Heterojunction. Have you heard about the word heterojunction before? If you're quiet means you know. So I don't have to.
Maybe.
Huh?
I don't remember.
Don't remember.
Homojunction? No?
Not sure, I think.
No, madam.
Okay. Heterojunction and homojunction is a junction like PN junction. It means that when you say junction, it means that there are at least two, what do you call it? Two materials together in the device. So homojunction means only one, the junction is using one single semiconductor material. For example, you can have a PN junction. PN junction is a device, right? And you can, the PN junction device can be from the same material. For example, this is silicon, this is also silicon. Okay, and this is called homojunction. I don't know if you, maybe I should put the, okay. Then another one is, you can have a PN junction as well, but the PNN, by using different material. For example, I would say this is, I will use the P, the P is silicon, the N is germanium. So this device, we call it silicon germanium diode. Okay, so you can, so this is called heterojunction. When you have two different material connected together, okay, heterojunction. So why I'm teaching this? This has relation to the okay. Because okay, now if I ask you to draw the energy band diagram for both this figure A and figure B, how does it look like? What's the time now? Okay, let's have 5 minutes. Draw. Can you draw the energy band diagram, zero bias, for this A and B? You understand my question? And I will ask you to share your screen. If you cannot share your screen, you just take a photo. Okay, I give you 3 minutes, 3 minutes. Are you listening to me or no? Senyap ni. Hello?
Yes, yes.
Okay.
Dengar.
All right, 3 minutes. Draw me the energy band diagram of these two, A and B. Let me give you another clue lah, kalau tidak susah juga for you. So let's say the band gap for silicon is 1 EG, for silicon is 1.1 EV. The band gap for germanium is smaller. I can't remember. Ni saya teka ya, bukan I can't remember. We need to open the table. Let's say 0.8 EV. Okay, can you draw the energy band diagram? I will call you within 3 minutes. Should try. Just draw and then if I call your name, I don't know whether if you put in the camera I can see or no, or you can take a photo, send it in the Telegram. Then we all can open it together.
Ini je lah.
Okay, I think time's up. So let's see, let's stop sharing here. So Anas, can you share your drawing?
Tak siap lagi tu.
Tak siap lagi?
Sikit lagi.
Sikit lagi. Siapa yang dah siap? Oh, video saya tak on. Nabiha?
Madam,
Sorry?
saya nak
Ambil gambar lah. Saya rasa kalau tak nampak aku cuba try. Cuba tak dekat kamera, nampak ke? Okay, definitely cannot see anything. So, okay. Baru nampak sikit. Tapi like, macam mana saya besarkan speaker view. Okay, can you do it again? Alamak, dia tak keluar pula kat speaker view ni. Kejap. Make you the spotlight video. Okay, I can see it. So, alamak, tak clear lah. So, what do you write on the band gap on the P side? What do you write on the band gap energy?
I draw the Venn diagram. Actually, I think it is almost the same.
Yeah, I'm asking you, answer my question.
The
I'm
difference is
asking
the
what do you draw for the energy band gap at the P side?
E side, silicon.
And the N side, what's the band gap energy? Energy band gap energy.
1.1.
Okay, on the N?
0.8.
Okay, does it reflected in the size of the band gap energy?
Yes. So that's why it is different. The
Okay,
silicon
good.
is bigger than yeah.
Okay, good. So that's correct. So brothers and sisters, if you do that, then that's correct. So basically, whenever I give, so you need to read the question carefully. It depends whether it's heterojunction or homojunction. It must be reflected in the drawing. So if it's 0.8, it should show a smaller band gap as compared to the 1.1. Okay, good. And sometimes, sometimes I want to make it trickier, just to check whether you are, what they call it, sensitive, cautious or no. I will also put different doping for the P and N, and that should be reflected. Okay, sometimes I put, okay, P, this is the number of concentration, and N is this. So it's always, when we draw, it's always relative. We don't know exactly how big is 1.1 eV, but it's relative. So if you can show some relativeness, it shows that you understand, okay, the concept. Right, so, okay, now let's go back to my screen, because the sister has answered for all of you correctly. Okay, can you see?
Yes.
Okay, so kenapa? Oh, sekejap. How do I do this? Okay. All right. So, okay. So now, okay, let's go back to this. So this is draw this back. So let's assume it's the same lah, although it's not very the same. So that's why when you draw, it's good to have a ruler with you, just to check whether it's the same. So since I'm the teacher, I want to make sure that you need to be roughly the same. Okay, so from here, you know, roughly it's the same band gap. So EV 1.1 EV, silicon is 1.1. If you want to go for interview for like semiconductor company, at least you need to memorize the band gap for silicon, 1.1 EV. It makes you look smart, just by knowing that, you know. Okay, so now, the question is, what happens after impact ionization, right? That was the question, right? Tadi siapa yang tanya soalan?
Yes, madam.
Okay, so let's use purple now. So this electron, so when it goes down, this is what we talk about, avalanche. For avalanche breakdown to occur, you need to have impact ionization. Avalanche breakdown. So we're talking about avalanche breakdown now. So for avalanche breakdown to occur, you need to have impact ionization. Basically, I think we need to exaggerate more, because impact avalanche, the reverse bias is very, you need to have a very large reverse bias. So when you draw, you need to be reflected as well. So let's make it extreme. Situ. Okay. I don't have a ruler with me, so it's typical roughly lah. Something like that. Okay. So then you have the end over here. So okay. So what happens is this electron that goes to the edge of the conduction band of the p side will drift. And because can you imagine, like it's like a ball, it's drifting at a very high speed. So so you need to imagine this now, the electrons are drifting, and it's hitting the atom. Okay, when it's hitting an atom, so you give energy to the bound electron holes. So when you give energy to the bound electron holes, you are releasing it to become free carriers. So you have extra electron and extra hole, because free hole is in the valence band, right? Free electron is over there. And the same goes here. So you have a hole will be drifting over here, hit atom. So you get free hole and free electron there. Okay. So when that happens, okay, so let's concentrate just on the electron not to make, because otherwise they're confusing. So it's the same thing that will happen but opposite direction of the hole. Then, so this electron, can you see here this electron here? Green, let's make it. This electron here. Now what happens is you have two electrons. Because the electron, which is the original electron that have been drifting, this one, and then you have extra electron because due to the impact ionization. And these two electrons will all still fall. Okay, will still drifting at high energy. And again, it will knock another atom and release electron hole pair. So it will keep on, and it will keep on drifting until it reach here. Okay, so when you reach here, okay, so this is avalanche breakdown, means in reverse bias. This is connected to negative, this is connected to the positive side. So the electron, when it reaches what happened here? Okay, when it reaches here, it will be collected to the outside world, right? To the circuit, and therefore you get current. So this electron, a lot of electrons. So when they arrive here, there are already a lot of electrons. that being collected due to this impact ionization, and these will be collected and then be measured by your emitter or something, and that's why you see a lot of current. Okay, and it's in the opposite direction of your forward bias, because forward bias, your electrons going this way. Now your electron going this way for reverse bias. Okay, have I answered your question?
Yes, madam.
Good. Any more question?
Will the material deteriorate after avalanche?
Will what?
Will the material break after avalanche breakdown?
Will the metal break?
Because we have the impact ionization, right?
Uh-huh.
So does it affect, will it affect the silicon or not?
Okay. 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 Good question. Okay, let's think about it. So you're asking whether the material will break. Is that what was that your question?
Yeah, something.
Okay, all right. So I just want to make sure I am hearing clearly what's your question. Good question. Interesting. So let's answer it. I'm trying to share. Okay. All right. So, okay, now you have your atom. Okay, you have this atom here. And now you have a high speed electron coming. Let's put the color purple lah. So high speed electron coming and hits this atom. Okay, and this atom has electron inside, bound electron and bound holes. So this hit and it will release electron and hole pair plus the electron that first hit. Okay, electrons are compared, the size of the electron coming. Okay, although it's at high speed, the size is actually extremely small. It's like a you can Google what's the size of electron compared to the atom. It's like the apa nama ni, the Earth orbiting the sun. So it's very small, very negligible. However, it can affect the atom only by giving energy to the bound electron hole. It will not affect the atom over here. The nucleus. So when we talk about the lattice, right? When we draw the lattice here, actually the circle one here is actually the nucleus. The nucleus is where most of the masses are, right? It's heavy. The atom is heavy, tak heavy pun. Berapa berat atom? The heavy kan, satu atom tu very. So but can you imagine how insignificant the masses of the electron compared to the atom, but still it has effect. But if the electron hits the the atom, because the nucleus is very heavy, it doesn't affect, so it won't lodge. Unless the other exception, extremely high energy of electron, and this one you cannot do in just normal lab or in your lab or normal house. That one may be possible, you may disrupt. Tapi normal case at reverse bias, that when we do even at 100 kilovolt or 1000 kilovolt, no, 1000 volt, even at 100 volt, 1000 volt, you still don't have effect. You have no effect to the atom. You just give energy to the electron holes. All right, have I answered your question?
So basically, it won't affect the atoms, but it would affect the electric.
Yes, property. Yes, it will just affect.
I think that's what I was trying.
Yes, it will affect the electrical properties. Not much of the physical structure. However, if you do research for my research, right, I do research on the effect of radiation, nuclear radiation towards a semiconductor device. So I have my FYP student doing that. So nuclear radiation can also have beta. Beta radiation is from electron. So a very high and very strong energy of the electron can give effect to the physical structure and will give defects. But for the purpose of this just reverse biasing, tak ada masalah. Alright, good. Any more question?
Madam.
Yes.
Tadi,
Siapa?
yes,
Who are you?
saya, Amirul Faris.
Amirul Faris. Sekejap, saya cari kat mana awak ni.
Okay.
Di manakah awak? Amirul Faris, yes.
Right.
Next to me. Okay.
You just mentioned due to the impact ionization, the electron that is released by the due to this process is going to give a lot of current. Right? How about the holes?
The same.
Also the same.
Yeah, also the same. But
Alright.
imagine the electron on opposite direction, the hole in opposite direction, but the current is the same direction, right? Because the different, although it's in the same direction, so we'll add up the current due to the hole and the current to the due to the electron will add up to become the same current in reverse because it's the same direction of current. Good. Any more
due
questions?
to your drawings, you draw that after the impact ionization, the electron and the hole that is being released, the electron is on the covalent bond sides and the holes is in
not covalent, conduction.
Conduction. Sorry, the conduction band and the holes in the valence band. Is it always happen like that? I mean, how?
Okay, good question.
Yeah.
Let me ask you. What do you think?
I don't have an idea.
No, you have a clue lah. I already teach you for 2 or 3 classes. Think about it. Why is it like that? Hazim nak tolong jawab. Hazim Salam. To answer. You think it's always like that or no or why? Hazim, are you there? Yes. Please.
Actually,
yes. What do you think?
I think sorry, but Amirul Faris, can you repeat the question? I need to rethink first.
Okay, repeat the question, please.
Right. During the avalanche, I mean, during the impact ionization process, when the electrons hit the atoms, it releases a pair of electrons and a pair of electron and holes. So my question is, just now, Madam just draw that electron is after the impact, the electron is on the conduction band while the hole is on the valence band. So my question is it always like that?
What do you think, Hazim?
I think is it always like that?
Why?
Because let's say the P side, it has the majority of the holes, right? Majority carrier is holes on the P side, so the holes will be in the valence band at the P side, and also for the N side, the majority carrier is the electron. So the electron will always be in the conduction band. So
Why
I think
electron always be in the conduction band? Why?
Because
Let's ask Nick Aizuddin. Nick, are you there? Thank you, Hazim. Nick. Oh, are you sleeping? Like, are you sleeping, Brother John? Okay, no, okay, dia macam stuck tu. Nick, are you there? Gambar ke video tu? Not sure. Let's ask Iqbal. Now, what do you think? Why electrons are always in the conduction band? Iqbal?
I think because in the valence band they are full of bounded electron, so no more electron can go to the valence.
Again, it's not clear. Repeat the last sentence.
Because at the conduction band they are full of bounded hole. That's why the electron go to the conduction band.
In conduction band, there are lots of bounded hole. Ya, kenapa buat cerita pasal hole? Kita cerita pasal elektron ni. Okay. Okay lah. I think you sort of having the idea, but the way you explain it is not clear. I worry in the exam you answer like that. I have a headache, if all of you. So try to answer directly. So to answer question of Amirul Faris, basically when the high kinetic energy electron hits the atom, it releases, it means impact ionization occur, and it releases electron hole. When it releases, these electron hole are free electron hole. So for it to be free, electron has to be in the conduction band and hole has to be in the valence band. So that's the answer. Because there are a lot of empty states, right? We talked about empty states before. All right. I think we have 10 minutes. I want to talk about your assignment. So your assignment, don't worry, the due date is after 2 weeks. And I'm thinking the assignment to be in groups, so to reduce your work. However, in your presentation, there will be group marks and there will be individual marks based on how you answer the question. And I'm expecting, and this is important, I'm expecting, even though you divided the subject matter into different people, but other people in the group have to know other people's work. You need to teach each other. So for example, one talk about how does it work, another one is parameter. I can ask the one who presented and how it works about parameters. And you should be able to answer the same as good as the other one. Okay? If not, and then I will cut marks there. So I will give full mark to everybody, then start, dah tak boleh jawab or not clear, I will start cutting marks. So let's share my slide over here. And the slides is in the link that I gave. You can go and look at it. It's in slide number 2. Share screen. Okay. Can you see my
Yes, madam.
All right, basically there are 4 assignments here, 4 topics: solar cell, light emitting diodes, LEDs, lasers, and photodetector. So there are 16 of you. I'm thinking to have only 4 groups. So 4 in a group. 4, 16 lah. The master student, you are honored. You'll be given what do you call it? One topic only. So Afiq, you can get laser. You have laser lah. You have the honor to have laser. And the rest of you now I think what we'll do is I want you to go, and I won't determine who will be in the 4 of you. So you need to determine on your own. Okay, so you choose your own group mates. And what does it cover? You need to explain what is it. What is a solar cell? What is a laser? What is light emitting diode? Okay, And this must be semiconductor solar cells, semiconductor light emitting diode, semiconductor laser, and semiconductor photodetector. Because laser can be gas laser. So I've had students before who suddenly, I was shocked. He explained about gas laser. Why in a semiconductor class that you want to explain a gas laser? We in a semiconductor class. So everything should be semiconductor. Even solar cell. Solar cell, there are organic solar cell where are not semiconductor. The one OLED, remember your TV is actually using OLED or organic LED. Organic LED is not using semiconductor, using like organic material. So the one that we want to call the LEDs here is semiconductor material. So please check your content before you present. Otherwise, I will deduct my half. If any, none of the semiconductor, I deduct half straight away. Then from there, you do more mistake. Cut. Okay. So make sure it's semiconductor. And you need to explain what is it. What is a semiconductor laser? What is a semiconductor photodetector? How does it work? Okay, when you explain how does it work, you need to be able to you need to explain it in terms of energy band diagram. So you can. So I highly encourage you to have slides. So when you present, you have slide showing, or you can, if you want to draw, you can also have a pen. You can draw like a whiteboard if you want. But it must be in terms of energy band diagram. I don't want you to explain in terms of the structure. Okay, you need to draw the energy band diagram and make your friends here understand how it works through energy band diagram. So for example, light emitting diode works in forward bias. Photodetector works in reverse bias. Laser works in forward bias. Solar cell, go and find out. Okay, so you need, so this all, if you learn, that's why when you understand my video, you should be able to explain the four. And if you don't understand, you can contact me before the presentation. During the presentation or after the presentation, I will not consider for the marks. I will just deduct marks. So if you don't ask me before. Then you need to also have different types of devices. What are different semiconductor lasers that you have? So you have quantum dot laser, quantum well laser. I think in next class, I will talk about quantum dot, quantum well. We'll talk about some, kita dah cerita lattice mismatch ke belum? Have we talked about lattice mismatch?
Belum.
Okay, we'll talk about that in the next class. So I'm just giving you earlier so you can start reading, gather information. So different types of devices, there are many. So so the way I will give marks, it depends on how detailed and how much you can cover. It depends. And you only have 20 minutes for each group. Okay, it needs to be very concise. Okay, different types of devices, 20 minutes for each group. So for example, what is it? It doesn't have to take like 5 minutes. What is it? It's like 1 minute. There are parts that you need to concentrate. And the most of the marks, the content, the majority of the marks will be how does it work. So if I were you, I will find somebody who are really good to explain how does it work. Okay, but I can ask anybody in the group about this, and your friends can ask, because as I mentioned, you'll be learning only through presentation. I will not have any class on this, so you should, your friends should ask you question and should be able to answer. If you cannot answer, I will try to answer, so for the purpose of learning. Performance parameters, this is also very important. How do I know a laser, the semiconductor laser is a good laser? If I want to buy a laser, what are the parameters that I should look for? Your mother want to buy a light emitting diode, go to pasar. How do I know? How does she know performance parameter, which one to buy? Okay, so that's the performance parameter for each one. So you should find out and then explain what is it. And current tech, you don't have to explain all the, if you want, you can put 1, 2 equations, but just to what do you call it, explain or make emphasis of the performance parameter, but you don't have to put any equation, just the understanding of it is important. And also current technology, maybe not many, 1 or 2 current technology. What is the current technology on lasers, semiconductor laser? Where are they going now? What are they doing? What are the materials they do? Okay, so this one you can Google. So make sure you reference it properly. I will share with you the rubric, okay, so that you know how do I mark this. I need to stop sharing. I have 2 minutes. Macam mana rubrik saya ni? Okay, let's see what's my rubric. Okay, I need to share again. I will share with you the rubric, insyaAllah. Rubric. Okay, so I need to share. Okay. Okay, can you see? Right, so this is the rubric. Ignore the seminar 2. So I change it a bit from seminar 2. So basically, understanding of the topic, 20 marks, and this is individual. I will ask question on this, and also when you explain your part. But it's actually a group work. So the technical content, I will give overall mark for the group. Presentation flow, overall for the mark for the group. Confidence and references also maybe overall for the mark of the group. Make sure you reference it properly. For every pictures that you have, you need to reference it, and whatever information you get, you should reference it at the back of the presentation. Okay, or deduct marks if you don't have. And also another part of it. Okay, I need to stop sharing that. Masalah pula. Where does it stop sharing? I want to share another thing is, let's go back to the slide. This marking criteria, roughly this is the rough percentage. Clarity, understanding, thoroughness of the topic, English usage, presentation flow, creativity. This Islamization, I will add into the rubric. You need to put some Islamization, your reflection of the Islamization inside the presentation. Okay, and this will be a group mark, Islamization. So as a group, you need to think, what is the Islamization that you can have for this? 20%, it's quite a lot. Okay, good. Any question? So I will give, this is already in slide 2 that I shared. Okay, any question? Now go and find the 4 of you. Next class, I will determine which one get which. We'll do some random picking. So so 4 in a group. If you cannot find your team, let me know. Okay, I think that's all for today. Thank you very much, everybody. And if you have any more questions, please write down. You can ask me in the next class, inshallah. So you need to really understand the forward, the reverse, because that is the basis when you want to explain the assignment, the laser, the forward bias, everything. Okay, and if you look at the resources, there is some in the internet videos on it, tak banyak on energy band diagram. So go and find out. Okay, I have students and master student before also post somewhere in the video so you can watch. Kalau ada lah, you cuba cari. Okay, good. Let's close the class with the doa. Can we have somebody to recite, please? A brother who haven't recited before.
Saya baca.
Okay, silakan.
Bismillahirrahmanirrahim. Alhamdulillahirabbil alamin wassalatu wassalamu ala asyrafil anbiya'i wal mursalin wa ala alihi wa sahbihi ajma'in. Allahumma inna astaudi'uka ma qara'tu wa ma fahimna wa ma hafizna faruddahu ilayya inda hajatina ilayhi innaka ala kulli syai'in qadir. اللهم أرنا الحق حقا وارزقنا اتباعه وأرنا الباطل باطلا وارزقنا اجتنابه. اللهم ارزقنا يا ربي فهم النبيين وحفظ المرسلين وإلهام الملائكة المقربين في عافية يا رب الأرحم الراحمين. اللهم زدنا ولا تنقصنا وأكرمنا ولا تهنا وأعطنا ولا تحرمنا وآثرنا ولا تؤثر علينا وارضنا وارض عنا. صلى الله على سيدنا محمد وعلى آله وصحبه وبارك وسلم والحمد لله رب العالمين.
Alhamdulillah Alamin. So thank you, Jazakallah khairan, Amirul Faris, for the dua. Let's close with tasbih kifarah and surah al-Asr. Subhanakallahumma bihamdika ashhadu an la ilaha illa anta astaghfiruka wa atubu ilaik. Bismillahirrahmanirrahim. Wal 'asr innal insana lafi khusr illa alladhina amanu wa 'amilus solihat wa tawasaw bil haqq wa tawasaw bis sabr. Okay, thank you very much. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam.